Deep Learning for Beginners, Theory and Application by Austin Glugla. So we'll start off with a brief history, a bit of a primer on the prerequisites of the course. We assume you know basic Python and maybe played around with a little bit of Keras, maybe a little bit of TensorFlow, and have general knowledge of at least some of machine learning and the algorithms therein. So prior to the 2000s, most of the research that was going on in neural networks was, architecture, right? We were finding new architectures, different ways of creating a connectionist model. As far as results, they were very few and far between, which, as you learn, is part of the reason that we had 2 AI winters and deep learning and neural networks in general took so long to take hold. Right, so the first neural network was a model created by Rosenblatt. It's called the perceptron. It's the simplest connectionist model. It consists of one input layer, one hidden layer, and one output layer, typically with one output neuron, but multiple are still considered a perceptron. The next real big event in the field took place in 1969 when Minsky and Seymour paper released a book called Perceptrons. And Perceptrons was a book that, among other things, contained a bunch of mathematical proofs on the models, Rosenblatt's models, perceptrons. And essentially what they said was the simplest perceptron model, so the one I just described to you, cannot learn the XOR function. This is correct, right? This is a mathematical proof that shows that a single layer perceptron cannot learn the XOR function. But the real big, you could say contribution, but I would say detriment to the field in general, was that according to their intuition, they believed that deeper or multi-layer perceptron models would not be able to perform an XOR either, which is just flat out wrong. We have models now and can provably show that neural networks and connectionist models are able to, in fact, perform an XOR. So post paper and Minsky's book, there was a big rise in symbolic approaches because connectionist models fell out of favor, mostly because of this book, right? Most of their proofs showed that these models were inherently limited. While that's not the case, it was their point, and you can essentially say they were trying to lead people away from connectionist models and neural networks. And this gave rise to symbolic approaches, stuff like rule-based systems, very simple models that don't have a lot of complexity and therefore, can't do a whole heck of a lot. And because of this, these symbolic approaches were only able to go so far. And this led to what was coined the first AI winter. And essentially what this was a drastic reduction in projects and funding in the field of artificial intelligence. And this was one of two. There's actually been 2 AI winters in the history of the field. I would probably say the first was a bit more catastrophic, to be honest, for the field. It's because we really pushed what are the most beneficial and effective models today far out of the majority of AI researchers' minds. And that obviously is not a good thing because, as we know today, neural networks are the primary tool in a machine learning engineer's toolbox, right? So after this, Rummelhart et al. Showed that a multi-layer perceptron can, in fact, solve the XOR problem. And he did this via backpropagation. This was the first instance of backpropagation in a paper, and we'll go into that a little bit more in detail later in the lesson. Okay, so following that, again in the 1980s, we saw a renewal in funding due to simpler yet very effective algorithms, which can work on even smaller data sets than the majority of neural networks. Those were, for the most part, support vector machines and random forests, which is an ensemble of decision trees. And their success actually led to another downturn in neural net research, which seems counterintuitive on its face, but as was the problem with symbolic approaches, these really only went so far and just failed completely on very complex problems. So, again, connectionist models were the path we needed to start heading down. I'm sure during this time, Minsky's book was still fresh in a lot of AI researchers' minds, and would be so until about the early 2000s. So a brief history continued. Following that AI winter, we saw renewal in funding. Slowly but surely, research teams started to see progress in new approaches and a little bit in neural nets, but not so much yet. So one of the big spurring moments in the revival of connectionist models and the start of deep learning as a field itself was probably the LSTM. So after its discovery in 1997, the LSTM, which is the long short-term memory unit recurrent neural network, that's a mouthful, it became competitive with these classic algorithms, not symbolic approaches, but things like bagwords models, things of that nature. They started to be competitive with those, and this led to quite a significant resurgence in connectionist and AI funding in general. Right. So after that, probably the second biggest, you could even say this was the biggest breakthrough in the field. 2008, 2009, the benefits of using GPUs was discovered. So for those unfamiliar, GPUs are the main hardware used in machine learning today. You can use a CPU, but it is breathtakingly slow, right? And of course, there are things like Google TPUs and NVIDIA, to a certain extent, has implemented something like that in their tensor cores that are in quite a few of their GPUs now. But GPUs are able to, not just double or triple training times, they speed it up by entire orders of magnitude. So, powers of 10. Generally, it's said that 2 orders of magnitude is the speed up, of comparative hardware, right? So same generation GPU, same generation CPU. And this is just, it's hard to understate how big of a deal this was, right? Because, models that took months or, even close to a year to train now could be done in weeks to month and, vice versa. Models that were taking weeks were now taking days. Models that were taking days were now taking hours. And, people could actually start trying to tack hard, difficult, complex problems in which the complexity of the model will be such that it takes, quite a bit of computation to train it correctly. In 2012, we saw 2 very important improvements. So Eduonix, probably one of the biggest, if not the biggest, neural net and AI researchers out there right now. He was with Google Brain. He then went to Baidu, and now he is doing deeplearning.ai. And essentially what he did using unsupervised deep networks, he got networks to classify higher level features such as cats or other animals, people in YouTube videos. So this was completely unsupervised, meaning that there was no labels on the data. The model was just told to look at these videos and learn the features on its own. So this was, unsupervised learning is still quite the stickler of the problem. We don't have models that we can just, throw at data and tell them to learn things about what they're looking at, right? We normally have to perform supervised learning, in which we give labeled examples to the neural network to learn from. And this was such a breakthrough because we didn't have to do that. It just learned these features on its own. And the other one was Krzyzewski et al. Hinton was a part of this paper as well. He created a regularization method known as dropout. And what that is you randomly drop out a proportion of the neurons in a layer. Let's say your dropout value is 0.4, you're going to drop out randomly 0.4 or 40% of the neurons in that layer. And, while this may seem fairly counterintuitive at first, it actually improves generalization quite a bit, because models are able to, it forces the data through new pathways in the neural net, right? So essentially the neural network has to learn to be smarter, right? In the way it's updating its weights, in the features that it's learning. So it will end up not only learning the features that are most important, but learning more important features, right? So using this newfound methodology, Krzyzewski et al., including Hinton, was able to win ImageNet 2012, a computer vision competition in which you classify about 1,000 classes, animals, faces, etc. This was, quite the breakthrough, because computer vision was an extremely hard problem in which the results were not very good for a long, long time, such that, around 2007, 2008, in response to the results of one of these competitions, ImageNet, in fact, a prominent AI researcher said, without significant improvements in the state of the art, models will struggle to push 60 to 65% top one accuracy, which means a model outputs a class probability distribution, and its top one would be, the class that it predicted with highest probability. And I believe Krzyzewski et al. Was able to do around 78 to 80% top one accuracy, which was just unheard of at the time. What Dropout allowed the model to do was stop overfitting, and overfitting is, if you keep adding layers to a regular feed-forward network without something like Dropout or other forms of regularization, it will quickly overfit, which means it learns a representation of the data that is much too close to the data set, and it's not able to generalize to new examples. So post that, the Atom Optimizer, AlphaGo, AlphaZero, capsule networks, GANs, there's been tons and tons of new architectures and methodologies, new intuitions that have pushed this data field forward. So quickly, just what is a neural network, right? A neural network is a connectionist, and connectionism is essentially networks or graphs that try to emulate in some way the mammalian structure of neurons. And ANNs are a type of function approximator. A function approximator in general is, pretty much what we're trying to do in machine learning. We're trying to learn an approximate function that can either predict a class or a regression value to a certain degree of accuracy. And this is a term that's more often seen in something like reinforcement learning. But yeah, just keep that in mind, because it's a term you might be hit with at some point. So next we're going to talk a little bit about the types of networks. Feedforward is the next simplest up from a perceptron. using everything from regression to classification to having a bit of use in reinforcement learning as well. And as you can see in the picture below, it's densely connected, which means each layer is fully connected with each subsequent layer. Right? Okay, so next we have recurrent networks, and these are by far the most useful and prominent networks in the field of, it's called a subfield of NLP, NLU, voice synthesis, etc. Pretty much anything to do with language in general, recurrent networks are what you're going to use. They also have a bit of utility in time series prediction. Right, so let's say, for example, you wanted to predict the price of a stock or a currency over time. This is a very good network that you would want to strongly consider and test. And this is mostly because it can learn time-based features, because information from the output layer gets propagated back to the hidden layers of the network, as you can see below. Next, we have a convolutional neural network. These are, primarily associated with CB, computer vision. They have a bit of use in reinforcement learning as well, even when you're not learning from, images alone, as, they did in the Atari models by David Silver, where a reinforcement learning model learned from scratch a plethora of Atari games. I think it was something like 25 to 30. And it learned that all from scratch from the images on the screen. But CNNs also much less frequently are used in reinforcement learning when you're just learning from a raw input vector observation. So, in the example of Atari, you could think of that like, what direction are you moving, how fast are you moving, enemy locations, etc. Right? Okay. So a few more. We have autoencoders. These are slightly different architectures in that we're trying to learn a compressed representation of the data. And that may or may not be somewhat obvious from looking at the architecture below. We have an output and input layers that are the same size. Normally in supervised learning or reinforcement learning, we're going to have an input vector that is the size of our data, and output dimension that is the size of our classes, or if we're doing regression, it's going to be 1. If we're doing reinforcement learning, it's going to be the number of actions that we can take, and that's going to be a linear activation there. And these are very interesting models because you can do things like anomaly detection, right? So, and you can do this in a semi-supervised way where you only have a few labeled examples. You train the model on your normal data, and it learns the representation of normal data. So I like to think of this in terms of like sound waves, right? So we're essentially learning the sound wave, that representation, and if anything doesn't fit that sound wave, it's considered an anomaly. They also have, quite a bit of other uses as well, things like dimensionality reduction, denoising, etc. So GNNs, they were another, breakthrough model that really pushed the state of the art forward. They're generative adversarial networks, and at a higher level, we have a generator network and a discriminator network. The generator is going to try and produce examples that fool the discriminator. So let's say, for example, we're trying to produce images of cats, right? The generator is going to try and produce lifelike cat images that fooled the discriminator into thinking this was a real image and not one produced by the generator, right? And, this is a very interesting, I would say brilliant intuition that led to this. in this way, you sort of can model different sorts of problems, right? Because you have a generator and a discriminator, and you're not, necessarily trying to learn from labels. Your error is computed, by the right and wrong guesses of the discriminator. And, that's a really powerful idea and something I think you should keep in mind. And another one that I thought of that's very useful, even today, for simpler problems that, you can find the optimal solution to, right? So Markov chain, if you run it correctly, will find the optimal solution. And it's just a graph of different nodes with probabilities that relate to actions or events. So you can think of this in the reinforcement learning context. That's probably easiest, where you have probabilities associated with each transition from state to state. Yeah. So just a few other architectures to perhaps look a bit deeper into. We have a Hopfield network, Boltzmann machine, extreme learning machine, and neural Turing machine. So the only network out of these that I've used is a Boltzmann machine, and it wasn't even, just regular Boltzmann machine. It was a stacked restricted Boltzmann machine. So in restricted Boltzmann machine, the nodes are slightly different, and it's stacked, right? So we have a bunch of Boltzmann machines stacked on top of each other. You can essentially, it's analogous to layers in a regular feed-forward neural network. I won't spend too much time on the other ones. Hopfield networks, don't have too much use today. ELMs and neural Turing machines, however, these are, fairly recent architectures, neural Turing machines in particular. We just got a open source model in 2018 related to this. So the intuition behind this and, everything else related to neural Turing machine is quite interesting. I encourage you to go, dig in, because I would say, in opposition to, normal deep learning algorithms, this is something trying to progress to something closer to artificial general intelligence, a general algorithm capable of solving any problem at the same level as a human. I really like neural Turing machines. I'm not going to spend any more time on them, but I do encourage you to do more research. So we're going to start simple. The main components or structure of a network are the input layer, the hidden layers, the output layer, the activation functions, optimization algorithms, loss or cost functions, and regularization. And we'll go over each one of them in varying levels of detail. Okay, so as you may or may not know, it should be rather obvious that the input layer is the first layer of any network, and there's only one for, any model out there in existence currently. That's not to say, and this is something I like to stress as well, it's not to say, an architecture with multiple input layers is not possible or it might even be effective, right? I try to convince people to get out of the box of deep learning and just, brainlessly applying the algorithms to the data sets because, one, that's not any fun, and two, you're not going to make any progress in the field that way. The goal of the field is AGI, and, simply optimizing or improving on deep neural network is not going to get you to AGI, right? It's just not. But, thinking outside the box, adding new components, switching architectures completely. These are the types of, pioneering ideas that will get us to that next stage. The input layer will have the dimensioning of your data. So if we have 42 columns in our data set, we're going to have an input dimension of 42. Same thing with computer vision. Well, if we have a data set of 256 by 256 images, our dimensionality will then be 3 by 256 by 256. And of course, the 3 is RGB. So one important note, when you're working through these problems, even now I like to keep, the fundamental ideas in my head when I'm working through a problem. And for example, if you're using keras, the input layer is implicit. So you're not going to define in its own line by itself unless you're using the functional API. It will be defined by the input dimension or the input shape. And let's say you make a dense layer with input dimensions of 50, that 50 will be the input layer and your dense layer will just be, a regular hidden layer. And another thing to take note of is the input layer does not form any calculations on the data or anything else, right? It's just the input. A hidden layer. So a hidden layer is where all the magic happens, right? It's sandwiched between the input and the output, so you can have n hidden layers. Typically these will be fully connected, but in certain models you can have sparsely connected neurons, particularly in autoencoders, but there are some architectures that implement it in a variety of models, from recurrent networks to convolutional, etc., etc., etc. And the hidden layers are where the concept of the black box comes from. I'm sure you've heard that, neural networks are essentially black boxes. That's not entirely true, but, for the most part, we can say it's trivially true. It's very difficult to derive what's actually going on in those hidden layers. It's very simple to see what's going on at the input, pretty simple to see what's going on at the output. But the magic that happens in between is, a major open problem in machine learning. So normally, all hidden layers will use the same activation functions. There are some exceptions. Sometimes in regression, you will use something like in a TAN with another activation function in the hidden layers, or in autoencoders, this happens as well. But in general, we can say that most models will have all these same activation functions in the hidden layers. And the deep and deep learning is just describing the number of hidden layers. That's where the word deep learning comes from. It's not, the depth of, the knowledge that the neural network is learning. It's simply just the number of hidden layers. And the output layer, it's the one that makes the prediction, whether that be class, regression value, etc. This layer will normally have a sigmoid or softmax activation for classification, and then for regression, we're going to use a linear activation. And that will be the same thing for reinforcement learning, unless we're trying to output action probabilities, action value probabilities. Then we will use a different output activation. But in general, we'll have a linear activation that has units related to the number of actions that you can take in a given state. And we can consider the hypothesis as follows. And I will break this down slowly. One important note is that the formalization below contains a bias unit. This can be a effective and helpful thing to do when training a neural network, which is tack on an extra neuron that is static at +1 or -1, depending on the problem. And what this will do is it will give some consistency to the updates of the neural network. So normally the weights in the neurons of a neural network are constantly changing. And, it can intuitively make sense that some sort of, linear regularity would be helpful in discerning amongst a bunch of dynamic variables, right? So at a high level, that's essentially what a bias unit is doing. And to break this down, Z of I is equal to our weights. So this is weight I and our X input. So another important thing to keep in mind as far as the formalization goes, so X1 at the input going to the next layer will then become X1 as the output of that neuron, right? So you'll have in X input example that changes as the data propagates forward through the network. And then we just add our ith bias on the end. And then our activation is simply just a function over that, right? So it's just a function over our weights, our input, and our bias. Pretty simple. And then we can formalize the hypothesis or the output as our hypothesis with respect to our weights and our bias is a function, so another activation function, over the output of the n hidden layers. What is an activation function? Good, I'm glad you asked. An activation function is what determines the output of any particular node. So as we saw in the previous example, we're running the activation function over the weights, the input sample, and the bias of our neuron. And that will, determine the output of that neuron into the next layer or into the output. All right. And the activation function is analogous to the action potential or rate of firing of mammalian neurons. So connectionist models in general are based strongly off of biological brains, and in particular mammalian brains. And, this is a perfect analogy for, the activation function being analogous to that rate of fire. So that's a very good higher level analogy to really click, a concept that can be as arbitrary as, an activation function or math, right? We don't have inherent meaning for a bunch of numbers and Greek symbols. And it's, again, I'm going to stress this quite a few times. It's important to be able to connect those higher level concepts to the math itself. So we have a couple different types of activation functions. One are linear. Mainly when you see a linear activation function, it's just, y equals x. It's very, very simple. Due to that simplicity, they struggle, to solve complex problems, because when we're thinking of a neural network as a function approximator of, whatever data set we're feeding it, if we have a highly nonlinear problem, which means the correlations between the input vector, so, our tabular data, our pictures, and the output, or our class, or our regression value, are, going to be linear, and they cannot model a nonlinear problem. That just, it won't work, right? And an important correlation to keep in mind is that a neural network with solely linear activations is essentially just doing linear regression. So if you ask, or ever wonder why not use linear activations in every single layer, it's because we're just doing linear regression then. So the majority of research and effectiveness of these models comes from nonlinear activation functions. This nonlinearity is key. Again, as I explained, you can't model nonlinear problems with, linear solutions or linear representations. That just doesn't make sense, right? You can't model a curve with a line. You can get closer and closer to an approximation of a curve with, lines ad infinitum, but you're only going to get so close. Okay. And one additional point of that is that you cannot model a curve with infinite straight lines. So even if you had infinite straight lines, you can't model a curve. All right, so next. The simplest activation function. We basically covered this already. A linear activation. Y equals X is what that is showing you right there. Next, we have a sigmoid. This is a quite common nonlinear activation function. It was used in hidden layers for quite a long time until we came up with better nonlinearities like TANs, like ReLUs, like ELUs, like Swish, Soft Plus, etc., etc., etc. There's tons of activation functions, as I will hit on. But mainly now they're just used in binary classification. And then we have softmax, which is just the generalization of a logistic sigmoid for multi-class classification. It's as simple as that. So a few more examples. We have the TAN that I briefly mentioned a bit earlier. It was quite common for a long time. It had properties that led to better convergence than using a sigmoid in your hidden layers. But with the rise of other activation functions, mainly ReLU, TAN really fell out of favor. So next we have the ReLU, simply a rectified linear unit. And after this was discovered, it really, really quickly became popular. It has a number of properties that improve convergence over, let's say, TAN, when applied in the hidden layers, and especially because it does not suffer from the vanishing gradient problem. However, there does emerge another problem with ReLUs, which is called the dead neuron. So once a ReLU is equal to 0, it's dead. So it cannot get further updates in value. It never fires. It's a dead neuron. It's just wasted computation and data. And there's a few ways to mitigate that, and some of the further optimizations that have other rectifiers such as ELU, GALU, etc. These have, for the most part, done away with the problem of a dead neuron. And then next we have Swish. It's a very simple activation function. It's a sigmoid over x times x. So we just our normal sigmoid function, and we're multiplying by x again. Intuitively, this probably performs better because you're getting a little bit of stability and updates because you're multiplying by x again after you apply sigmoid over it. However, there's not too much higher level analysis of the Swish activation function, as it's fairly new, starting to see a good amount of use, but it's still rather on the cutting edge. And as you can see here, it does do much better than ReLU on a variety of problems. So a couple others that we'll go over quite quickly. GALU, this is a brand new activation function, the details of which were published in November 2018. According to the white paper, it performs better than ELU and ReLU on every test they tried it on. However, it is extremely new. I would suggest, trying it out if, you have a problem that it doesn't take too long to train and you can do quite a few different iterations of models and, play around with things. This is definitely an interesting thing to try. There's not too much out on it, but it does look very promising. So Soft Plus is essentially just a smooth ReLU. It looks a lot like a ReLU function that was smoothed into a curve. Just check it out. It never became too popular because its efficiency and convergence properties aren't that much greater than ReLU. So it wasn't too much of an improvement over anything. Soft Plus, ELU, this is another powerful rectifier. It has very interesting properties. As you can see, it's a little bit different than a normal activation function. More closely models a normal neuron where, we're essentially using different functions over X if the value is greater than or less than a particular value. And then binary step, these were never that useful, but they are important to understand if only for, at a higher level, getting to know, these sort of if-then activation functions where we're applying a different function over X based on the value of X. So these are becoming slightly more popular with ELU and things of that nature. Nothing that has really, broken through to the top of the ranks like ReLU or even Swish to a certain extent has, but it's an active area of research and something to keep in mind and look into. So next we have optimization. What is an optimization algorithm? So in machine learning, optimization is the way by which a neural network computes its weights and generally learns, right? So this is a much more general concept than machine learning. Optimization is done in a wide variety of subfields in mathematics. You can consider, to a certain extent, machine learning and all of computer science a subset of mathematics. But optimization is essentially just updating an underlying function towards some ground truth, or in reinforcement learning, it's known as optimality or the optimal solution. All right, and then this is a very important concept at the foundation of all of connectionism, machine learning, AI, and neural networks in particular. Hinton is very big on backpropagation, as he thinks that humans do it in some form or another. And it's by far the most prominent way to compute the gradients of a neural network. There's really nothing else that is used. So some examples, we have SGD. That was pretty much the first optimization algorithm to be used in neural networks with backpropagation, and it arguably still is the most popular. It performs effectively, not necessarily efficiently, on pretty much any problem you throw it at. Very versatile, very good convergence properties, if not the quickest. However, as we get further along, I will explain a bit more of that in detail. So next we have the atom optimization function, and this is just a bit of a tweak on stochastic gradient descent, in which we have an adaptive learning rate based on some parameters that are adjusting your training. And one really important thing to keep in mind, and this is being researched more and more last year and this year, the convergence properties of atom are not as great as they at first seemed. So atom tends to converge to a local minimum much more often than SGD, and tends to oscillate much more near a local minima or global minima as opposed to converging to it. So oscillation in this context is if we visualize the gradient descent algorithm, just essentially a hill, some slopes, those dips are the local minima and the global minima is the deepest dip. The gradient will cause the value to oscillate, above that local minima, and it will never converge to it. So RMS prop is one of those functions that really just was gone as soon as it appeared. So it was popular for a very short period of time after he presented it in off the cuff just in a lecture. He later formalized in a white paper, but it was quickly, taken over by Adam when efficiency and convergence properties proved superior to it. But I'm sure, there's certain problems where every single optimization algorithm might do better or worse than another one. Okay, so the next part of a neural network that we'll cover is loss and cost functions. So what is a loss function? Loss function computes the cost. So this is analogous to the error rate on a given prediction or event. And it's what our optimization algorithm is actually trying to minimize. And this is just the opposite in reinforcement learning, where we have a utility function and we're trying to maximize reward over n time steps. It's also known as a reward function. There's quite a few different types. There's Bayesian, frequentist, regret, entropy-based, etc. One very important thing to keep in mind is cost functions are much more specific to problem domain and problem type than, let's say an activation function or an optimization algorithm. For the most part, loss functions will only be used in a certain class of problem and, aren't useful outside of it. So a bit more on that. As I said, only certain functions will play well with a problem class. So, we'd use binary or cross entropy loss on a classification problem, but if we were doing regression, we would have to use something like mean squared error, mean squared logarithmic error, which just takes the mean square over error. But something like log cosh in regression, for example, can kind of take the best of both worlds with respect to MSE. So what log cache essentially does is act like MSE, except when you have an incorrect prediction, which can throw off MSE quite a bit and lead to an oscillating problem that I talked about earlier, where the network oscillates around a local or global minima with respect to the optimal solution and never converges. And a couple other examples of those, would be focal loss for classification, mean absolute error for regression. And there's, tons of loss functions. I would do a bit more research because that's one of the areas you can squeeze out a few extra points of accuracy, right? So let's say you just use MSE intuitively when performing regression, right? Maybe if you plugged in log cache, you might get a couple extra points in accuracy, and that leads to hopefully a more general model that can predict better on new examples. And one of the last topics we will cover is regularization. So what is regularization? Regularization is a method by which we try to improve the generalization accuracy of a neural network or model in general. This can be done in a few different ways. Mostly, we are going to either apply them directly to the weight matrix or the actual units themselves in the context of dropout. So normally, regularization will reduce model complexity or the number of learned parameters. And, intuitively, this may not seem like would produce a better model, but what we're doing is, hopefully, in theory, reducing the number of less corollary features for higher. So the features that we do learn have much higher correlation with respect to our final output and the correct class than thousands of extra features that actually don't have much of a correlation at all. And it's as simple as that. So the three main regularizers that you will probably face when starting a career in machine learning is dropout, L2 regularization, and L1. L2 and L1 are quite similar. What dropout is essentially in a class of its own. I explained a little bit on dropout earlier. We take a proportion of the neurons in each layer, and depending on what our dropout parameter is, let's say it's 0.5, we will drop out half of the neurons randomly, and then the next we will drop out another half randomly, and this forces the data through new pathways in the neural network and ends up in a smarter network that hopefully is learning much greater correlation between its learned parameters and the ground truth. L2, on the other hand, is a term applied to the weight matrix itself. So down there I have the equation, and let's just take 30 seconds and walk through what the math is telling us. So lambda in this equation is our regularization parameter. This is what you will define yourself, and if we plug in 0 for that, it would essentially just be our loss function again, and you can work that out and see that that's true. But what we're doing is summing over our weights. We're taking the squared sum over our weight matrix and our regularization parameter lambda. And similarly, L1 is just taking a sum over our weight matrix, but we're taking the absolute value of that with respect to our lambda regularization parameter. So just the key difference between L2, L1, one is taking the squared sum, one is taking the summed absolute value. Pretty simple. So last slide. Conclusion and challenge. So what did we do here? This lesson was a brief overview of the history of deep learning as a subject, the structure of neural network, and the components therein. We learned about optimization, which is the method by which we work towards a ground truth function approximator. We learned about regularization, by which we improve generalization through either reducing model parameters, or in Dropout's case, it can also reduce model parameters, but in Dropout's case, we're just randomly dropping out neurons in order to get smarter gradient updates. We also did a little bit on activation functions, which are what determine the output of each neuron. We talked a little bit about loss or cost functions, which are the way by which we produce our error term. And that's how we decide, not us, but the neural network who is doing the optimization, whether or not we are getting closer to the ground truth with respect to our data. And then, again, simply we just went through each layer, what it does, and put it all together. I have a challenge question. At the end of each of my lessons, I'll propose a little challenge question to better grasp the topics that we covered in the lesson and, do a bit of further exploration into what we covered. As with pretty much any subject, there is always more to know, there's always more to learn, and there's always more to discover. So don't let this be, the end-all be-all resource. Go ahead and, read more, apply it. And, that, in my opinion, is the most important thing you can do. You take these concepts, these very abstract concepts, and apply them to real problems. And that's how you're able to truly understand. That's how understanding happens, when you can take a concept and either apply it to a problem, without having your hand held, or, you can teach it yourself. That's, probably the next level of understanding. I would say, application and teaching. But as a student of any subject, an important part of the learning process is, continuing learning and expounding on what you already know. And with that, the challenge question today is on backpropagation. And backpropagation, as learned earlier, is the method by which we compute the gradients of our loss function. And this was something that personally helped me understand backprop, intuitively and in a way that, I wasn't able to do before. A lot of modern machine learning frameworks will abstract away what's going on in the network to the point where, the concepts can stay abstract and not really be understood. And that's part of the application step, right? In order to truly understand any concept, you have to be able to apply it, and this is right among those lines. Here, I want you to read up on backpropagation, understand the maths on the forward pass, the maths on the back pass, to the best of your ability, however long it takes, 20 minutes, an hour, a few hours, whatever. Take the time, if you're up to it, work through the math, try to conceptualize it, try to break down the equations at a higher level, and then apply it to yourself in raw Python and NumPy, right? So this is a challenge that Andrej Karpathy, one of the top AI researchers in the field right now, came up with, and he makes his students do every semester. And that's, to really understand the concept, you have to implement it from scratch in, essentially raw Python. NumPy gives you a little bit of abstraction, but not such that you don't understand what's going on. And so that's that. Implement the forward and the backward pass of backpropagation in a function using raw Python and NumPy only. If you think you've done it, you think you have the right answer, go ahead and check it. I gave a link at the bottom that actually implements the raw forward and backward pass in NumPy and gives, quite a bit more information than I could possibly cover here. It's a long write-up by Karpathy, who's top in the industry. I would highly recommend it. All right, so I'm signing off for now. I will see you in the next lesson.